How's it going, guys? If you came here from the first lab review video, welcome. If this is your first one that you're starting out with because you already know everything about Lab 9, also welcome. I'm going to be talking about heat and enthalpy changes for chemical reactions. In the first video, I did go over some things that may be helpful, like working with percent error and also labeling your units and a brief explanation as to why you should. So if you're looking for that, go ahead and check out the other video. And if you're just wanting to focus on heat, stay with this one. In the next video, I'll be working with titration, and then on Lab 12, which I hope that you all will be in person for, we'll be working on stuff in class for that, because I do need to brush up a little bit on how Lab 12 is done first, before I try and tell you about something and tell you that it's wrong. So, starting with Lab 10, heat. We worked with an equation in class, which was Q equals MCAT. I'm going to show you that one real quick. This is our equation. It can also be rewritten as Q equals SM delta T, with our S being our specific heat. If you want to write it as S or you want to write it as C, it doesn't matter. I'm going to be using the C version because that's what I grew up learning in high school and college. So let's go ahead and get started. First, let's break down a fundamental. If you have a system, you can expect that any transfer of heat in that system, if you were to track it going out or in, it should neutral out to zero, because you cannot create or destroy energy, heat being a type of energy. So if, like we were working with metal, really hot metal and water in the lab, if you take your heated metal and you stick it in the water and it heats the water, you can expect that transfer of heat to net to zero, because you can't get rid of anything. Even though you're getting rid of heat from the metal, it still isn't the same as completely annihilating it Thanos snap style. I'm surprised that my dog didn't hear anything about that, because his name is also Thanos. And no, I did not name him that. So let's break down the equation for our Q equals MCAT. So our Q is going to be our heat or energy of heat in a system. For this, I'm going to track the heat lost from a metal. That way we can sort of understand it a little bit better. Breaking this down, the heat of the metal that is lost, our mass is going to be the mass of our metal. If we know what that mass is going to be, you can use balances, of course. Or, you know what, I'll leave that for physics. Just the mass in grams. C is going to be our specific heat. Hold on, my computer is telling me to update my computer. There's no update, it's 10 years old. C, specific heat. That is going to have a specific value, much like our R value in Lab 9, that is going to tell us how to do the rest of the equation, which I will tell you about in a minute. Our delta T is going to be our change of temperature, and because this is a difference between two temperatures, it doesn't matter whether or not we have it in degrees C or Kelvin, because both of those units take up the same amount of space. 1 unit of Kelvin is the same as 1 degree Celsius. Now, it doesn't mean that they're at the same level, it just means that they take up the same amount. It's like how Fahrenheit is just a little bit smaller than Celsius. So, let's break down our C value. Our C value, being our specific heat, is going to have a very particular set of units that sit at the end. So for this one, what I'm going to do is I'm going to use degree C, just to kind of give the idea that when you're doing the addition, subtraction, that you're using degree C. My unit for C is going to be joules divided by grams times degrees Celsius. Now, if you were presented with an equation like this and you were given C, immediately all of your values have to line up with this. So if you're given like kilograms of a certain like material, if you're given the moles of a certain material, you need to find that in grams. If you don't, your math will be jank, your answer will be wrong, and you'll lose some points on the exam. When it comes to degrees of temperature, what you're going to want to do is you want to take that final temperature minus the initial temperature, and whatever that difference is going to tell you what the relation is in your specific reaction. So in this case, my final temperature for my metal should have been lower. My initial temperature for the metal should have been higher. That being said, I am going to have a negative difference of temperature. That's fine, because I am losing heat to the system. So thinking about it this way, right? Just so I can sort of explain through why. I have a negative difference of temperature. All my other things don't really matter in this case because you can't have a negative mass. You would break physics. And your specific heat can't be negative because that would be kind of weird. And now my other dog, Sisu, is here to see me, which we did name. So looking at this here, I know that I can't have a negative mass. I know that I can't have a negative specific heat. So whatever negative here is on this temperature, I'm going to move it over to my Q. I know that I'm going to have a negative on that side. Very important to know this because when you have a negative Q, it means that you're losing energy. But you're not just losing energy to lose energy, you're losing energy to a different system. In this case, we're getting it in the water. So if I was to, I'm going to label this metal, and then I'm going to make a new equation for my water. In that case, instead of having a negative, because I'm not losing anything from the water, I'm losing things from the metal. But where's that heat going? Well, it's going to the water. So in that case, I'm going to be gaining heat. I'll find my mass, my specific whatevers. And because my final temperature of water should be higher than my initial, I'm going to have a positive T value. Of course, I can't have negative water, and I can't have negative specific heat. So at the very end, I should have a positive Q value because I'm gaining energy there. Very important distinction to make if it's sort of hard to work through or think about in your mind. Go ahead and do some equations, go back through and do lab 10 again, and just plug in some random values. Probably should keep the specific heat and the mass the same, but you can change up the temperature changes just so that you can understand how that relation works. I think for this one I will also be posting in the description a few links to videos that will help you sort of understand how to work through that. And if it still doesn't work through with you, probably take a second, drain all that information from your brain, go have like a brownie or a cookie or something, and then come back and try that again. But completely blank space, like you're learning it again. Because I know that for organic chemistry, and I know I tote that a bit as like, oh, I took organic chemistry. There's much harder forms of chemistry that you may want to take, like physical chemistry, transport chemistry. The list goes on. Chemistry is a very big profession. So organic chemistry, one of the things that I had to approach, because I wasn't very good in Chem 1. I wasn't at most of the classes. I thought I could breeze by because it's organic chemistry. It's about carbon. Well, that wasn't the case. That one I really had to study for, and so I barely scraped by with a B, I believe. Going into organic chemistry 2, I did much better. Reason being, I had to approach it with an open mindset. There was no more thinking that, oh, well, if it was like this before, it's going to be like this again. I had to completely relearn the topic. So if this is a very difficult concept for you, which for me in high school it was, go to it with a blank slate, come back to it empty-headed. There's no thoughts outside of this specific equation. There's no preconceived notions of what you're actually working with. Just come into it completely new, completely fresh, and try and pick through it yourself. I guarantee you it will be way more beneficial than me just sitting here and telling you about it. So, since that was really most of our lab, I'm going to go ahead and talk through why we may want to convert something into kilojoules afterward. So, in the beginning of the semester, we talked about using our significant figures, right? We have only so much space to actually hold numbers, so we want to sort of break them down and hold them in a smaller area. That is specifically tied to our bigger units. So whenever we find this equation, we found the Q, and our values are really big, like in the 46,000s, the 50,000s, or sometimes even the 2 millions. We may want to break down that value into smaller amounts so that we're not doing calculator math on paper. So in that case, you're going to go straight to your units, and you're going to convert joules into kilojoules, gigajoules, whatever you really need to. I think megajoules is the conversion for 10.6. Don't quote me on that. I still need to look that up. I haven't had to convert that big because I do small experiments like this. So in this case, I'm going to convert to kilojoules. I'm going to take that 50,000 divided by 1,000 and get that 50 kilojoules of energy. For this example, I'm looking at an equation right now, and my specific heat has 4 values, my mass has 3 values, my temperature has 3 values, so really what I'm going to want to go with is the 3 values. Taking a 5 value option, because those zeros after the 5 will still count because they're taking up that space, if I break that down and I take away that extra 1,000, I can now have 50.0 kilojoules because those number of significant figures will fit. I believe that is really all that needs to be said for this part. I probably should talk about why baking soda is a bit more important to use as opposed to sodium hydroxide when it comes to picking up acid spills or even on a person. So this post-lab question here, it asks if you spill hydrochloric acid on your skin, which will burn after a little bit, and it's incredibly corrosive. If you were to wash the area with sodium bicarbonate, baking soda, and water, it asks you to explain 2 reasons why the sodium bicarbonate is much better than sodium hydroxide. In the lab, I know that some of the values weren't exactly correct, but your math was. When it comes to using sodium hydroxide in HCl, that's going to create a lot of heat. Reason being, that is giving off a whole lot of energy, and it's a very strong base and a strong acid. It is going to completely dissociate, break the bonds, give off heat, water, and salt. So now you're going to have a really hot, salty solution. I don't know if you've ever put salt on a wound, but it doesn't feel the greatest. So if you're going to use your sodium hydroxide to clean up a hydrochloric acid spill on you, one, you may have this leftover sodium hydroxide solution on your skin that can also continue to burn you. But you're also creating heat, which doesn't feel the greatest, especially if you're having a big jump of heat, which may feel like it's burning, and salt on a wound just doesn't feel good in the first place. So moving on to our sodium bicarbonate, if you are using that, first thing you need to understand is sodium bicarbonate is a weak base. It's not going to completely dissociate immediately. It's going to take a very long time. As you should have seen in the lab, it took a long time to stir in the sodium bicarbonate as opposed to the sodium hydroxide. At least when I was preparing for a lab, I think it was last week, we were going to teach some children. We were trying to find a way to do a different sort of luminol solution that involved sodium bicarbonate. I found myself stirring that solution for around 20 minutes, whereas opposed to stirring a sodium hydroxide solution, it only took me about 5 minutes. So a very big difference in how weak bases and strong bases work. So that being said, your weak base, you can use extra. The baking soda we know is not toxic to humans. You can have that extra on there, you can put it on in excess so that it reacts with the HCl completely. It will create a cooling effect, as should have been noted in the lab, but it's not going to dissociate as fast. It's not going to create that extra heat because that sodium bicarbonate may also be splitting and coming back together. It's reabsorbing that heat in those bonds. So another thing to note with that, it is a endothermic reaction. It's absorbing that heat. Endo meaning in, thermic, of course, referring to thermal or heat. When you're using NaOH, it's exothermic. It's exo meaning out, thermo, of course, meaning thermal, so exothermic, giving off heat. So if you were to use baking soda on a spill, it would be much more beneficial to you, at least your skin, because you're not going to burn through it incredibly quickly, and you can apply extra. And really all it takes to wash off sodium bicarbonate is water. So you pretty much kill 2 birds with 1 stone there. So that is all for lab 10. I will go ahead and move on to lab 11, which is titration. I will do that in a different video though, and I'll go ahead and leave this off here. Just a reminder, if you're working with your equations, especially your Pivnert or your Q equals MCAT equations, excuse me, I just had breakfast, you're going to want to follow the units that are stated in that specific value. Convert every other number that you have into those units. That way it flows a whole lot easier than if you were just to go into it with your random mass, your random temperature, your random pressure even. You want everything to be lined up exactly how you want it. I will try to put extra videos in the description of these videos just to show you the different concepts, have someone else explain it to you in case me explaining it doesn't necessarily work. But anyway, be safe. Do not drink glue. It is bad for you, even Elmer's glue. It's sticky and it's disgusting. So don't do that. All right. See you either on Monday or I'll see you in the next video.